Welcome to this fourth video in the lecture series on NMR spectroscopy. What we've done in the previous video is we've looked at concept of chemical shift and all the factors which affect a chemical shift in detail. What is the topic of discussion for this video will be a very important concept called as spin-spin coupling. And this spin-spin coupling also happens to be very crucial in structure elucidation when it comes to NMR spectroscopy. Okay, before we move ahead and start looking at spin-spin coupling as a concept, let's just focus a little bit on the chemical shift concept which we came across in the previous video. Now, it is very important for us to remember that these chemical shifts are highly local structure dependent. So if at all you look at a certain nuclei and probe its NMR, then its local environment or the local substructure is going to determine what the chemical shift value is going to be. And this helps us because you could go on giving incremental values based on presence of certain groups in the substructure, and based on that you'll be able to make a prediction of what should be the chemical shift value for a certain nuclei when it is housed in a certain localized environment. And that's what helps in automation. And now there are many softwares which are available in literature which, when you input the structure of a certain chemical that you want an NMR spectra predicted of, it will give you a predicted NMR spectrum with all the couplings involved, splittings involved, as well as the chemical shift values for various nuclei that is present in that particular molecule. Alright, so what you see here is an appendix from the book Pavia, which details how increments can be given to certain groups when they are present at certain positions in the molecule, and based on these incremental values you'll be able to make a prediction on what exactly should be the chemical shift for a certain nuclei. And you do see that there is a good correlation between the actual chemical shift values when the NMR is recorded experimentally versus that is computed based on the empirical values of increments given to certain groups. What you see here on the right is a software called nmrdb.org. It's a website, and this site also helps in giving you predictions for NMR. It in fact has options for both H1 as well as C13. What it asks you to do in this applet is to put down the structure of the molecule that you require a predicted NMR spectrum of, and once you hit the simulate spectra tab here, it gives you an NMR spectrum that is predicted with the splittings involved, as well as the exact chemical shift values that you would see for various nuclei that are present in the molecule. Okay, so that brings us to the concept of spin-spin coupling, and any detailed discussion on couplings and interactions between the spins of nuclei that are nearest neighbors, etc., requires us to also discuss beforehand equivalence and non-equivalence of nuclei with respect to NMR. So it's important for us to understand that those nuclei which are in identical environments, localized environments, will be termed as equivalent nuclei, and those nuclei which are not in identical environments, there is some difference in the environment with respect to the electronics and the magnetism involved around the nuclei, are called as non-equivalent nuclei. Okay, so the equivalence against the non-equivalence can be made out based on a factor called as spectral isochrony versus anisochrony. Okay, so those peaks which appear at exactly the same delta ppm value, those nuclei which resonate at the same delta ppm value in a molecule, are called as spectrally isochronous because they give a signal at the same delta ppm value for those many number of nuclei that are present in the molecule. Okay, so we've got that concept of spectrally isochronous versus spectrally anisochrous for the NMR spectrum. Okay, so these peaks which are isochronous are also called as coming from nuclei which are magnetically equivalent. Okay, so that brings us to the next concept of magnetic equivalence. So when their magnetic environments are the same, then you will get the peaks to appear at exactly the same delta ppm value, and you will call those nuclei as being magnetically equivalent. All magnetically equivalent nuclei are also chemically equivalent, and chemical equivalence comes from distinguishing that particular nucleus or that group by using some chemical reagent. So if a reagent is unable to distinguish between two different sides of a molecule or two different substructures in the molecule, then you would call them as being chemically equivalent. Let's take an example to understand this concept better. Say for example, we are looking at a molecule of isopropyl alcohol. In isopropyl alcohol, you have two terminal methyl groups which are chemically indistinguishable from one another. So if you use any reagent that can transform the terminal methyl group into some other group, then it may do so at either of the two methyl groups because they are both chemically indistinguishable. In this case, these chemically equivalent methyl groups also possess protons which are magnetically equivalent. But we should also bring about this distinction right here, that all chemically equivalent nuclei may not be magnetically equivalent, because magnetic equivalence requires the structure to be exactly identical, even with respect to the stereochemistry, and the overall electron cloud around the nucleus has to be exactly the same. Otherwise, you would see some minor spectral anisochrony between the two nuclei. So magnetic equivalence is much more rigorous a criteria that needs to be fulfilled by a certain nuclei to be called as magnetically equivalent. Whereas for chemical equivalence, the criteria is a little more relaxed as against the magnetic equivalence. So once again, what I'm trying to reinstate here is that all magnetically equivalent nuclei are also chemically equivalent, but the vice versa is not always true. So all chemically equivalent nuclei may or may not be magnetically equivalent. Okay, to sum up this discussion, what we've done so far is we've established what are equivalent and non-equivalent nuclei, and we furthered this discussion by taking it one step ahead and saying that equivalent nuclei can either be magnetically equivalent or chemically equivalent, and what is the difference between them. Right? Now, another very important concept is that only those nuclei that are magnetically non-equivalent can couple. So now we are establishing criteria for coupling between nuclei. Okay, so only those nuclei that are magnetically non-equivalent are capable of coupling with one another. The next criteria is that they should be in the vicinity of each other so that they can affect each other's magnetic properties. So two criteria have to be met rigorously so that nuclei can couple with one another. One of them is that they should be magnetically non-equivalent, and secondly, they should be in the vicinity. And I'm using the term vicinity and not neighbors, because they could be in the vicinity either through bonds. So I could have an example wherein I have a certain nuclei being probed which has nearest neighbors with respect to bonds as two different types of nuclei here that I'm labeling as A and B, both of which can couple with CH2 because they are in close proximity to this nuclei being probed with respect to the bonds that they are separated by. There is also a possibility that in some cases you could have nuclei that are very far from one another with respect to the bonds, but are in close proximity to each other in three-dimensional space, and these nuclei also tend to couple with one another. So vicinity is only in space such that the two nuclei can affect each other's magnetic properties. So the criteria to couple is that they should be magnetically non-equivalent, and they should also be neighbors such that they can affect each other's magnetic property. Only such nuclei are capable of coupling with one another. Now, what happens when two nuclei couple with one another? The same peak that is supposed to have appeared at a certain characteristic delta ppm value now appears in the form of certain grouped peaklets. So rather than seeing a single peak, you would see certain groups of peaks appearing because its magnetic environment is affected by its nearest neighbors. And the way the neighbors affect the peak splitting pattern of this nuclei that is being probed can be given by a relationship called 2ni plus 1. So the number of peaklets that you would see for this nuclei being probed based on the number of neighbors, if the number of neighbors that are affecting its magnetic environment is n, given by n, then the total number of peaklets that you would see would be given by 2ni plus 1. Now this formula 2ni plus 1 is wholesome in that it applies for any nuclei that you may wish to probe. So irrespective of whether the nuclei has a half integral spin of half or 3 by 2, or whether it has a complete integral spin of 1, 3, 5 and so on, for all types of nuclei you will be able to predict how many what will be the coupling pattern and how many number of peaklets will be observed for a certain peak when it is split. All that can be probed just by applying this formula of 2ni plus 1. This formula empirically gets reduced to just n plus 1 in case of proton and other nuclei where the I value is exactly half. Because when you substitute I is equal to half in this formula, you get 2 multiplied by n multiplied by half plus 1. And this formula just gets reduced then to n plus 1. So if at all you see in standard books this formula, empirical formula of n plus 1, that can help you in making a prediction of how many peaklets you would get for a certain peak when it couples. Remember that this is a simplification from the formula that holds universally, which is 2ni plus 1. Now the question we may be interested in is that why should there be splitting of the signal that should be observed? And let's try and understand that a little better by using this example of ethyl iodide. Now say for example, if we are probing the spectra of this molecule according to the H1 NMR spectrum experimental design, you would see that there are two magnetically non-equivalent protons, one set belonging to this methylene group which we've labeled as A here, the other one which is a set belonging to the methyl group labeled as B here, right? Now each of them form their own characteristic set of magnetically equivalent nuclei. So there are 3 magnetically equivalent nuclei which should appear at some characteristic delta ppm value. Here you have a delta ppm value of 1.83 for the protons that we've labeled as B. You've been given another set of peaks appearing at 3.20 for protons labeled A. It is consistent with our discussion on chemical shifts in the previous video, because the protons on of the A type are directly attached to an electronegative atom, that is iodine, and hence it's logical that it should be shifted a little downfield as compared to the methyl protons which are labeled B here. Okay, so now what is the question at hand is that why should the peaks due to B be split by the signal of A, and likewise why should the signal of A be split by peaks due to B? Now to answer this question, let's pay a little bit of attention to the possible spin arrangements that have been given with respect to the neighbors. Now this is the splitting pattern for the methylene group which is there at the center here. Now this methylene group has three neighboring protons, which will also affect the magnetic environment around the nuclei of the protons that are a part of the A group. Okay, so there are three nuclei as a neighbor that's present adjacent to this particular methylene group, which will affect the magnetic environment of this methylene group nuclei. Okay, so how can the arrangements be? The arrangements can be that you have the three nuclei which are neighbors, all of them having a spin that is represented by plus half, because now for this nuclei you can only have two different arrangements, right? You could have either a plus half or a minus half spin states. We've come across this in our very first video wherein we talked about the number of different spin states depending on the overall nuclear spin of the nuclei. Since the nuclear spin is half, you can only have plus half and minus half two spin states possible for a proton. Okay, so all three protons which are of the B type could be having the same spins of plus half, and plus half, and hence right at the bottom you've been given plus 3/2 as the overall spin that will be having some effect on the methylene protons then, right? There is another possibility wherein two out of these three nuclei could have one type of spin and one of these three could have the other type of spin, and there are three different ways in which you can attain such a overall spin for the methyl. That's represented by plus half here. Likewise, you have another spin state represented by minus half, and right at the end you have a minus 3/2 over here, right? Now each spin state of the neighboring protons which are forming a group B will have an effect on the resonant frequency of the protons belonging to set A when it is being probed in the NMR spectrum. Okay, so if at all these protons which are a part of B have the same magnetic moment as that of the applied magnetic moment, then you would see that the effective magnetic moment that is experienced by A is going to be slightly greater than what is being applied. So there is going to be some upfield and downfield shifts that will be observed to the tune of whatever number of nuclei are present as its neighbor and affecting the magnetic environment around the nucleus as a part of the A subgroup. Okay. Now another, so this is what is the origin of peaks being split, and when the peaks are being split you get the total number of peaklets here. You can account for the peaks to be split into 4 peaklets. Now these 4 peaklets will have certain ratios, as is very clear from this particular example, that all of these peaklets don't have the same heights, and their heights have to do with the relative abundance of each spin state. So you have the middle 2 spin states which are thrice as abundant as compared to the terminal spin states, and therefore the ratio in which the peaks get split up can be given by 1:3:3:1. So when a quartet is formed, quartet of peaks is split, then you get the splitting pattern to be consistent with this particular intensity ratio, which is 1:3:3:1. So we've looked at what should be the basis of this particular spin-spin coupling that should result from nearest neighbors of nuclei which are in a magnetically different environment from that of the nuclei being probed. So once again, looking at this example of ethyl iodide, if you look at the protons which have been clubbed as A here, they have neighbors that have 3 protons on them, the B type, magnetically B type nuclei on its neighbor. So if we apply the condensed formula of n+1, you'll get 3+1, which is 4, and hence this nuclei will be split into a quartet. Applying the same thing to the terminal methyl group, you have 2 protons on the neighbor and applying the n plus 1 rule, you get 2 plus 1 is equal to 3, and therefore the B set of or magnetically equivalent nuclei will be split into a triplet. Okay, what we also came across in the previous slide was that the splitting into a triplet or into a quartet does not happen with each of these individual peaklets having the same heights, as the number of spin states representing each of these peaklets are not the same in number. And if they are not the same in number, they don't record the same intensity on the NMR spectrum. And this ratio of peak heights can be given by the coefficients of expansion of this binomial, which is 1 plus x raised to n. And as you go on increasing n from 0, 1, 2, 3, so on, you keep getting a large number of terms, and the coefficients of these terms will then help you in understanding what should be the ratio of individual heights of these peaks that are split from the main peak. A simpler way or a simplification to that is the Pascal's triangle, and all of this holds for H1 NMR or for any other NMR wherein the I value is half, and hence the splitting pattern does work out to n plus 1 and not the typical 2ni plus 1. So in the Pascal's triangle, you have for a singlet, if it is just a single peak, it will get split into a doublet provided there is a neighboring one proton that is available that is interfering with the magnetic environment of this particular peak. It will be split into a doublet, and the intensity of the doublet will be 1:1 according to the expansion of the binomial as well as from the simplified Pascal's triangle. When you have a triplet, the triplet will be of the ratio 1:2:1, which is what we've observed in a large number of spectra that we've come across. In case of a quartet, it is 1:3:3:1. This is the typical example. Then you have 1:4:6:4:1 and so on. If you see in the Pascal's triangle, the number that appears in the middle is just a sum of the two other numbers in the preceding sequence, which is directly above it. So this 3 comes from addition of 1 and 2, the 6 comes from 3 plus 3, the 10 comes from 6 plus 4, and so on. That's how the Pascal's triangle is a simplification, so that you don't need to physically expand the binomial using certain formulae and then predicting what the coefficient should be. You can directly get them from this sort of a framework. Alright, let me close this video with two interesting trivia that you may have observed in a C13 spectrum. Now I'm getting a little ahead of myself, but I'm sure that all of you have seen C13 spectra. And if you've noticed, wherever you see a solvent peak, typically where the solvent happens to be CdCl3 to record the C13 spectra, you'll always see triplet with equal intensities there. Something which is strange, because in the previous case in Pascal's triangle, we said that a triplet results with the intensity of 1:2:1. And that's why I reinstated that Pascal's triangle as well as the binomial expansion should be used only for protons or nuclei which have the spin equal to half. For nuclei that don't obey that rule, you'll have to physically look at the various spin states that are available and use the more comprehensive rule of 2ni plus 1 so as to judge the number of peaklets that you would get. And in CdCl3, the peak that is splitting the signal of carbon atom is a deuterium, and the deuterium has a spin value of 1. If you substitute 1 into this formula, you get 2 multiplied by the number of deuteriums in CdCl3 is 1 multiplied by its spin quantum number, that's 1 plus 1, that gives 3. And that's why in CdCl3 the solvent peaks that appear while you record a C13 spectra happens to be a triplet of equal intensities of 1:1:1. Okay, that's something which is interesting. Another thing that also you might find a little interesting is the concept of multiplet skewing. So routinely when you record NMR, you often don't see the terminal peaks to be of equal intensities when otherwise, based on your Pascal's triangles or based on binomial expansion, is predicted to be the same. But they are usually not the same, and that's something significant. Whenever there are two nuclei which are magnetically non-equivalent and are coupling one another, they are skewed in the direction of each other as they couple with one another. So if you see a pattern wherein this one is skewed in the upward direction here and this one is skewed in the upward direction towards the left, you can conclude safely that these two could be the nearest neighbors and hence could be coupling the peaks of one another. So if you find the coupling constant values the same and both these peaks skewing towards one another, you can reasonably predict that these two peaks have come from protons that are nearest neighbors of one another. That could help in structure elucidation. Alright, so what comes next is a very important concept of coupling constant, and we are going to devote some considerable time in studying coupling constants and how it can help us in getting some useful information while making structure elucidations from NMR.